I have differentiated 4 basic concepts here. Let us begin with the first one. That is, all solid and liquid surfaces at all temperatures emit thermal radiation. I repeat, all solid and liquid surfaces at all temperature emit thermal radiation. And this emission will be in the form of electromagnetic waves. And according to my Stefan Boltzmann law, it is the rate of emission per unit area is directly proportional to the fourth power of the absolute temperature. And the temperature here will be given in terms of Kelvin, and the rate of emission per unit area will be in watts per meter square. And also, I should know that the continuous spectrum of all wavelengths, and also it does not require a material medium for propagation. For that, as I said, wavelength of electromagnetic waves. This very first sentence gives me for all the temperatures, I have electromagnetic waves which has been emitted. B. This is my diagram for the electromagnetic waves. The thermal radiation will always be within 0.1 to 10 microns. This is on the x-axis. I have 10 raised to 0, 10 raised to 2, 10 raised to 4, 10 raised to 6 in microns. Then for me, the thermal radiation will always be in between 0.1 to 10 microns. Okay. Then lesser than 10 raised to minus 2, I'll be having gamma rays and X-rays. And greater than 10 raised to 2, I'll be having microwaves and radio waves. The visible light, for me, it will be within 0.4 to 0.7. Say, for example, for a visible light, it is an electric filament light, which is visible visible light. It will be in 0.4 to 0.7 microns. When I say the thermal radiation, it is in 0.1 to 0.7. That doesn't mean that it is only within that range itself. So when I draw a graph, with respect to the wavelength and with respect to this uh, electromagnetic waves, I draw a graph. The graph will be increasing with the increase in the wavelength, and to certain extent, it goes to a maximum, and then it starts reducing. And when I put the 2 points here, the limits, if I put the 2 limits here, it will be most of the area which is there within this curve, it will be within 0.1 to 10 microns only. The other part, we have radiation, but it will be almost near to zero. This part also, it will be almost nearer to zero. This part and this part also, it will be almost nearer to zero. So the wavelength, for all the wavelengths, I'll be having the emission coming out. But when I have a limit from 0.1 to 10, most of the area which is below this curve comes under 0.1 to 10 microns. So for which what we do is we consider we consider thermal radiation in between 0.1 to 0.1 to 10. So that doesn't mean it is not there below 0.1 and it is not consisting of above 10. We will be having radiation. So for us, the first basic concept is For all solid and liquid surfaces, all temperatures, thermal radiation will be existing. Along with that, the thermal radiation which is emitted will be in the form of electromagnetic waves, and it will be a continuous spectrum for all the wavelengths. And also, the electromagnetic waves which are coming out, it does not require any material medium for propagation. For propagation of these waves which is been emitted from the electromagnetic in the form of electromagnetic waves, it does not require any material medium for propagation. So that is what I should know in the very first class. Then this is about the emission. The second basic concept is about the surface which is been taken up. So in addition to emitting radiation, the surface of a body has the capacity for absorbing all or part of the radiation emitted by surrounding surfaces and falling on it. I repeat, in addition to emitting radiation, the surface of a body has the capacity for absorbing all or part of the radiation emitted by surrounding surfaces and falling on it. Say suppose for example, this is my surface. I'm considering this as my surface. Surrounding this surface, I have three other surfaces. I have three surfaces. These are my surrounding surfaces. I call these three surfaces as my surrounding surfaces. And this is my surface. These three surfaces are emitting rays in the form of electromagnetic waves, and they are in all the directions. Out of these, there are three waves which are falling in place. So it has a capacity of, this surface will always be having a capacity of absorbing all what is falling on the surface or part of it which is falling on this surface. So always a surface not only emit rays, it also has a capacity of absorbing the rays of all the rays which is falling on it or the part of the rays which is falling on it. So that is what the capacity of this surface. Say for example, one more example, I take one small surface. I take a small surface, I call it as S, and it is maintained at a temperature Ts. This small surface is being enclosed by an enclosure, and I call this enclosure has a temperature of Tc. And say for example, let this Tc be less than Ts. That is, the surface temperature is having a greater temperature than this enclosure. In that case, what happens is, I have a solid body S emits radiation because it is at a temperature Ts. I have a solid surface. This solid body will be emitting electromagnetic waves, that is the radiation, because it is at certain temperature. And also the solid body, whatever the solid body I have here, whatever the solid body I have here, it also intercepts and absorbs radiation. It also emits and absorbs radiation emitted by the walls of the enclosure. Okay, that means the surface is also emitting radiation towards this enclosure, and since this enclosure is also at a certain temperature, this will be also emitting certain rays from this end, which will be falling on this solid surface. Some of the radiation will be falling on this surface. So along with the emission, it also absorbs the radiation which is emitted by this enclosure. In that case, some part it is emitting and some part it is absorbing. If say suppose this is 1 and this is 2, 1 is greater than 2 because it is at the higher temperature and this is at the lower temperature. That in that case I have this body, whatever the solid surface I have, it will be cooling down because the radiation which is emitted is more compared to the radiation which is absorbed. So the body, what it happens, it cools down to certain extent. So in this manner, the heat transfer takes place. And according to my first basic concept, the last point of it, the last point of it, it it is nothing but this one. It does not require any material medium, does not require any material medium for propagation. That is, in between these two surfaces, I have a material medium. Say, suppose I can consider it as air, I can consider it as a liquid, whatever it is. But these emitted rays, which is emitted from this surface to this enclosure, it does not require any material medium. Let it be air or let it be liquid, or even if it is a vacuum, the rays will be emitted from this surface to this enclosure. So that is what my first point means, and the second point means it will be not only emit rays, it also absorbs rays, all the rays or part of the rays which is been emitted by the surrounding surfaces, and it is being absorbed or part of it or all the rays which is been falling on it by the surrounding surface. So that is what my second basic concept. Then the third one is with the directional nature. In the directional nature of thermal radiation is a surface emits radiation in all directions encompassed by a sphere. It doesn't mean that. This means I have a surface. So I'm considering only a small surface out of my surface. If I consider a small surface, which is at a certain temperature, it emits rays. So all the rays, I've shown it in the arrow marks. So these are the rays which are coming out. These rays will be nothing but in the form of, it forms in the form of a hemisphere. It will be encompassed in the form of a hemisphere. All the directions, if I consider all the directions, it forms in the form of a hemisphere. So it is the third basic concept for me is the directional nature of the thermal radiation. How my radiation will be coming out from the surface. It will be in the form of a hemisphere. If I consider all the rays coming out of the surface, it forms as a hemisphere. So that is my third basic concept. Then I come to the fourth one. That is, we shall be concerned only with situations involving radiation exchange between surfaces in which space between the surfaces is a vacuum or is occupied by a gas which does not participate in radiative exchange in any way. That means that in our further studies, whatever we are going to consider is there is a material medium between the exchange between the two surfaces, but this material medium we consider either it as a vacuum or we consider this as a air medium. If I consider this as a air medium, I'll consider this as a not participating in any of the radiative exchange. If I consider this as a air medium in between these two surfaces, I'll be considering this as non-reactive material medium which does not participate anyways between the radiative exchange. So for us purely radiative exchange will be between the surface from one surface to the other surface. For our studies in our future of this subject, we are only going to consider only that much. So for which I repeat the fourth basic concept, we shall be concerned only with situations involving radiation exchange between surfaces in which space between the surfaces is a vacuum or occupied by a gas which does not participate in the radiative exchange in any way. Okay, so these are the four basic concepts which we have studied. The first one, let me repeat it once again. The first one is at all the solid and liquid surfaces at all temperatures emit thermal radiation, and this thermal radiation will be in the form of electromagnetic waves, and these electromagnetic waves is nothing but it is a continuous spectrum of all the wavelengths, and this thermal radiation does not require any material medium for propagation. And for us, majority of the thermal radiation will lie between zero point 0.1 to 10 microns. The second basic concept, in addition to emitting radiation, the surface, it has a capacity of absorbing all or part of the radiation emitted by the surrounding surfaces falling on it. That is the second one. The third one is the directional nature. The surface emits radiation in all directions encompassed by a hemisphere. It is encompassed by a hemisphere. And the fourth one, we shall be concerned only with situations involving radiation exchange between surfaces in which space between the surfaces is a vacuum or occupied by a gas which does not participate in radiative exchange anyway. So this is my fourth basic concept. So let's start with the first one, the emission characteristics of the surface. We need to know, we have two things here. One is emission characteristics of the surface and absorption characteristics of the surface. As because the first concept talks about the emission characteristics of the surface, and the second basic concept talks about the absorption characteristics of the surface. So we have different concepts. So the first one, we will begin with emission characteristics of the surface. Before we know that, I should know what is a black surface. Black surface, it is, we call this black surface as an ideal surface which absorbs all the radiation falling on it regardless of its wavelength or direction. Say for example, this is my surface. This is my surface. I have a surface, and if I call this surface as a black surface, this surface will be absorbing all the radiation which is being fallen on this surface regardless of the wavelength and the direction of that uh, uh, waves. Okay, so that type of a surface we call it as a black surface. I repeat, it is an ideal surface which absorbs all radiation falling on it regardless of its wavelength or direction. For a given temperature and wavelength, a black surface also emits maximum amount. I can also take this black surface, absorbs all the surface which is falling on it, it also emits the maximum amount of energy which is there within the surface for a particular wavelength and a temperature. If I consider, say for example, it is at a particular wavelength and it is at certain temperature, it emits the maximum energy which is there within the surface. So that type of a surface, we call it as a black surface. So that is my first point here. The second point is total hemispherical emissive power. The second one is, the definition is total hemispherical emissive power. Some textbooks, they have taken it with a small e, and some textbooks, they have taken it as capital E. It is nothing but it is total hemispherical emissive power. It is defined as the radiant flux emitted from the surface of a body, and it is given by watt per meter square. I repeat, the total hemispherical emissive power is the radiant flux emitted from a surface of a body, and it is given by watt per meter square. Say for example, I take this as a surface. This is a surface for me, and I consider this surface at a particular temperature, and it is emitting rays in all the directions, and it will be encompassing a hemisphere. When it is doing so, the radiant flux which is coming out from the surface of a body is called as a emissive power. The radiant flux which is coming out from this surface is nothing but, it is nothing but the emissive power of a surface, and it is given by watt per meter square. Okay. Along with this, I have a total hemispherical emissive power of a black surface. Say for example, it is nothing but that is not a difference. Total hemispherical emissive power of a black surface, it is nothing but it is the maximum emissive power of a surface. Say for example, I consider a black surface and it is emitting rays in the form of a hemisphere, and these radiant flux is nothing but the emissive power of this surface. And if I consider this as a black surface, it is the maximum power which is being emitted from the surface of the body. So I call this emissive power, it is denoted by EB. I have taken small e, so I am writing small EB. Small e is nothing but total hemisphere of a total hemispherical emissive power, and EB stands for total hemispherical emissive power of a black surface. So E is emissive power and B stands for the black surface. Then the third concept is nothing but total hemispherical emissivity. Total hemispherical emissivity, it is nothing but it is the ratio of total hemispherical emissive power of a surface to the total hemispherical emissive power of a black surface. That is E by EB at the same temperature. It will be at the same temperature, E by EB. E is nothing but it is the ratio of E by EB. E is nothing but total hemispherical emissive power of a surface, and EB is nothing. Then this is denoted by epsilon. The total hemispherical emissivity is denoted by epsilon, and this will always be within 0 to 1. Emissivity will be always within 0 to 1. Okay. The next part of the is monochromatic hemispherical emissive power. Monochromatic hemispherical emissive power, it is given by E lambda. It is nothing but the radiant flux emitted per unit wavelength. The radiant flux emitted per unit wavelength. So it is being denoted by watt per meter square per micrometer. So E lambda is nothing but the radiant flux per unit wavelength, and this will be given by E will be equal to E lambda into D lambda. So E lambda is the quantity which when integrated over all wavelengths yields to E. That is, this E lambda in the other way to explain the emissive power, it is nothing but E lambda is the quantity which when integrated over all wavelengths yields E. So for me dE, I integrate these two, this equation on both the sides, and I'm integrating it over all wavelengths. So it is between 0 to infinity. When I integrate this with all wavelengths, it will be 0 to infinity E lambda d lambda. On the other side, dE when integrated, it will be nothing but E. For me, E is nothing but a total hemispherical emissive power. Total hemispherical emissive power will be given by which when integrated for all the wavelengths, E lambda when integrated for all the wavelengths will be given by the whole total hemispherical emissive power. And monochromatic hemispherical emissive power of a black surface, I call it as EB lambda. I call it as EB lambda. Say for example, I am drawing a graph with respect to lambda and E lambda. This is my E lambda, which is given by watt per meter square micrometer, and this is the lambda, which is given by microns micrometer. Then I draw a graph from 0 to infinity. It will be always starting from 0. It reaches to maximum to certain wavelength, and then again it starts reducing. And we know from the first basic concept, most of the thermal radiation, it will be between zero point 0.1 to 10 microns only. So in that case, if I'm going to take one small part of the wavelength, so I'm taking it as d lambda, a small part of the lambda, if I take it as d lambda, then this will be nothing but dE. So E lambda will be nothing but the emissive power uh, dE by d lambda. So this will be nothing but dE is equal to E lambda into d lambda. When I do so, I have, this will be for me, it will be nothing but, for me, the integration of 0 to infinity dE is equal to 0 to infinity E lambda d lambda. Integration of dE will be E with the same integration limits. So it will be integration of 0 to infinity E lambda d lambda. Then the last part of the emissivity is, I have a monochromatic hemispherical emissivity. It is nothing but again given by epsilon lambda. It is given by epsilon lambda, and it is the ratio of monochromatic hemispherical emissive power to the monochromatic hemispherical emissive power of a black surface at a same temperature and wavelength. I'm going to consider it for the same temperature and wavelength. So I call this as a monochromatic hemispherical emissive power. Okay, and say for example, if I draw on the y-axis E lambda and EB lambda, and in the x-axis the wavelength, and when I plot a graph, obviously because EB lambda is my surface, black surface, it will be having the maximum emissivity. So it will be having the maximum emissive power, sorry, not the emissivity, maximum emissive power when compared to E lambda. That is, so it will be having a higher graph. EB lambda will be having a higher graph when compared to E lambda. And for a particular wavelength, I draw a line. So I'm considering certain wavelength from 0. I draw a line, and this point I can take it as A, this point I take it as B, and this point I take it as C. So epsilon lambda will be nothing but A to B. A to B is nothing but for the normal surface, and A to AC is nothing but for me the black surface. So monochromatic means in some textbooks they have written as spectral. So don't be in a confusion. So because of that I have written the spectral. Monochromatic is equal to nothing but it is a spectral. So for me, monochromatic hemispherical emissivity is nothing but the monochromatic hemispherical emissive power of a surface to the monochromatic hemispherical of a black surface at same temperature and wavelength. And the last one of this emission characteristic is nothing but I have a gray surface. It is nothing but a surface having the same value of epsilon lambda at all wavelengths. I have a same epsilon lambda for all the wavelengths. Say for example, I am drawing emissivity from 0 to 1, and I have along with the x-axis I have a lambda, that is nothing but a wavelength. So for me, the emissivity of all the surfaces will be nothing but it will be varying in between 0 to 1. So I draw all the graph here.